Hello, my name is Adrian Stein and today I'm going to present you my conference paper on the topic Input Shape Control of a Gantry Crane with an Inertial Payload. This is a Gantry crane. A Gantry crane consists of a movable overhead structure which is able to move in 2D and a hoist which heaves heavy payloads. The payloads we are looking at are pipelines, which are used for offshore oil extraction. As engineers, it is our responsibility to guarantee the safety of the operating crew and to avoid property damage. Here you can see my outline. In the beginning, I start with the motivation and I'm going to show you a video. Then I will explain you how I modeled the whole Gantry crane. Then I will come to the simulation and in the end I conclude the results of the conference paper. This video is illustrating the profound dangers posed to a crew by a poorly operated crane. At the outset, everything seems normal and 5 crew members are trying to control the payload. But only one is holding a rope in his hands. Soon, the crew is starting to realize that the payload is uncontrollable, and they panic. Probably the worst moment to panic. The inexperienced crane operator is incapable of comprehending the complex crane payload dynamics and creates a potentially catastrophic situation. This impact can even be felt at the camera's location. And if this guy wouldn't step over the payload, he would probably already be dead by now. So I asked myself the question, can we come up with something safer than what we've just seen in this presentation? Can we create a safer working environment for the operating crew? And the answer to the question is yes, we can. By using the Lagrangian energy-based approach and identifying the natural frequencies of the system, we can apply a technique which is called input shaping. This minimizes the swinging of the payload and the twisting. Any problem to be solved requires abstracting the problem in the correct way. Unlike many solutions in the literature, we are posing a problem as such. We assume that the payload has a moment of inertia and that the rope which connects the hoist and the payload has a torsional stiffness. Let me introduce you to some variables which are used to model the crane payload system. This is the mass of the crane and the mass of the payload. Accordingly, for the payload we have an outer radius RO and an inner radius. Furthermore, you can see that we have a torsional stiffness of the rope, as I mentioned earlier, and a length of the payload. This is the offset of the center of the mass for the payload, and the rope length LR, which is changing over time. This is reference frame A and is a body frame, which is located at the hoist. We need 2 swing angles and 1 twisting angle. For the first swing angle, we're going to rotate around vector A1 as such, and this results in the swing angle delta, and in a new reference frame, which we denote as B. Let's keep B aside. Now we need another swing angle by rotating around the vector B2 as such. And this is basically just pointing vector B1 down to the payload and results in a new reference frame which we call D. Let's keep D aside. Finally, we have just one more task to do, and this is figuring out how we model the twisting angle. This can be done by just rotating around vector D1 as such and results in a new reference frame which we call F. This is trying to emulate the environment as realistically as possible. Our aim is to A. lift the payload, B. move the payload above the vessel, and C. to lower the payload. And obviously, we would like to see that the payload swings and twists as few as possible, right? Let me conclude what we have achieved so far. We know that we have a hoist and a payload, and we need 2 swing angles and 1 twisting angle. Swing angle delta as such, and swing angle epsilon like so. In the end, we have a twisting angle theta, which looks like this. The controllers for the hoist are going to be applied in X and in Y. Let's keep this sketch on the side. Here you can see my controller, which I applied to the hoist, where you can see that X, Y, and the rope length are just PD controllers with the following parameterization. Furthermore, I need to mention that the payload starts at the initial position of 0, 0 and is going to be moved to 5 and 12.5. Input shaping is a technique which cancels its own vibration. This is that vibrations excited by a previous part in the command are getting cancelled by parts which are later in the command. In a block diagram setting, input shaping looks like such, where the input shaper is placed in front of this box. From the transfer function, we can see that input shaping is basically just a time delay filter, where A0 and A1 are amplitudes and can be calculated by the damping ratio. The time delay t can be calculated in closed form from the damping ratio and the natural frequency of our system. For robustness, we just need to put 2 or more input shapers in series. Here I chose 2 input shapers. The only mathematical extra effort which we have to do is just squaring the transfer function. The third controller I'm going to present is a Minimax controller, which consists of 2 time delays, as you can see here. The amplitudes and the time delays can again be calculated in closed form as soon as these 2 frequencies are known. Let me emphasize that the input shape controller is just applied to the x and the y direction and not for the rope length. And for simplicity, we assume that the center of the mass for the payload is currently 0. The red dashed line and the red payload are showing the normal PD controller, while the solid blue line and the teal payload are showing the input shape PD controller in a non-robust setting. To my right, you will see 3 graphs evolving as soon as I start the simulation, where the 2 upper graphs are showing the swinging angle and the lowest graph shows a twisting angle. Wouldn't it be cool to dive into the crane operator's view to see the twist of the payload? That's why I created this bird's eye view, which illustrates the twist of the payload better. In the beginning, both payloads get lifted and then moved above the vessel. You can already see that the normal PD controller creates significantly more vibrations of the payload. However, the input shape PD controller is creating a significantly quieter working environment. A large twist can be observed from the normal PD controller, which can be as well verified by the bird's eye view. The question is, how can we compare the swing angles and the twisting angle of both controllers in the best way? The method I chose is the difference between the maximum and the minimum angle value for each angle respectively. The swing angle delta could be decreased by 66% and the swing angle epsilon by 63%. The biggest achievement could be recorded in the twisting angle theta, which resulted in a 95% decrease. If you look at the control inputs, we can really understand what input shaping is doing. Remember, the reference was moving the payload from a 0, 0 position to a 5 and 12.5 position in x and y. Therefore, the PD controller, which is normal, applies an instant force which decays over time. However, the input shape controller is splitting this force into 2 peaks, as you can see here and here. This is due to the time delay. I should note that for the normal PD controller in red, we can see some oscillations in the control input for the rope length. And this is due to the fact that the controller is trying to compensate for the swing and oscillations during the maneuver. As seen in our simulations, input shaping worked so well because it was designed for a certain rope length during the maneuver. Assume now that crane operator A is moving the payload at 3 meters, crane operator B is moving maybe the payload at 7 meters. So as control engineers, we need to account for uncertainties in the system. Therefore, let's make the rope length LR and the center of the mass of the payload uncertain. Now I'm going to compare the non-robust with the robust input shaper. And remember that the robust input shaper was basically just putting 2 input shapers in series. This marks the uncertain rope length during the moving maneuver, which varies from 3 to 7, and this marks the uncertain offset of the center of the mass for the payload, which I set from -1 to 1. As a comparison method, I'm using again the difference between the maximum and minimum angle value for each angle respectively. For delta, you can see that the non-robust solution is getting easily outperformed by the robust solution. For the swing angle epsilon, we can observe that the robust solution is outperforming the non-robust solution just by a little bit. And this is a result because our x reference was way smaller than our y reference. Remember, 5 to 12.5. And that's why swing angle epsilon doesn't show such a big decrease with the robust solution compared to swing angle delta. Last but not least, a robust solution is outperforming again the non-robust solution for the twisting angle theta. We observed that the robust solution is outperforming the non-robust solution in any case. And therefore, I want to now compare the Minimax design to the robust solution. When the color is red, the Minimax design is outperforming the robust design. When the color is dark blue, the robust design is outperforming the Minimax design. For all 3 angles, we can see that the Minimax design is outperforming the robust solution at the corner points, meaning when the uncertainty of both variables is at its highest. For instance, here, here, or here. However, for the nominal design point, the robust solution is outperforming the Minimax design, which lies in the nature of a Minimax filter. So let's conclude what we've achieved with this work. First, we were able to model the payload with a moment of inertia, and we introduced torsional stiffness for the rope connecting the hoist and the payload. Second, we could see an enormous twist reduction when we apply an input shape PD controller compared to a normal PD controller. And third, we performed a sensitivity analysis with respect to an uncertain rope length during the moving maneuver of the payload and an uncertainty in the payload center of the mass. We would like to thank the National Science Foundation, and for a further discussion, please feel free to reach out to me or to my advisor. Thank you.